Good morning, everybody. Hello, Carderock family again. I'm actually here at my place of rotation at Naval X. I'm still a Carderock employee, so I'm still there, but I wanted to welcome you guys into the webinar for Engineering Week Part 2. Thank you guys for joining the webinar last week. I hope you were able to catch the replay. If not, the PAO, I believe, is sending or already sent out the video on how to view it. Just some logistics. If you guys have questions, please direct them to the question and answer chat, but we always love interactive webinars. So, in the chat, if you guys want to discuss what the topics are all about, please enter them in the chat. But you guys are welcome to ask questions using the question and answer function. So welcome to part 2 of Engineering Week. And I'm going to give Dave Drazen the ability to take it away.
All right. Thanks, Ashley. So I'm Dave Drazen, Carderock CTO, and I'm excited. Last week was a great discussion on cognitive diversity, and I think today is just going to be as exciting. We're going to have a triumvirate today of Dr. John Holmes, Trish Shields, and Dr. Craig Lawrence, and I know it's going to be exciting, covering the gamut from talking about Dr. Holmes's patent to trust in AI, which is an important topic. There's a lot of conversations around AI ethics, but I think trust in AI is just as important, probably more relevant to Carderock and the work that we do. So I'm not going to belabor the point. I'm going to turn the floor over to Dr. Holmes, who's Carderock's Distinguished Engineer for Underwater Electromagnetics, and he's going to be talking about his patent called WILMA. So John?
Thank you. Let me bring it up. Let's see. Share screen. Okay. This is one of, I've lost count. I think I have 14 patents right now, but this is one that's sort of in the middle of all of them. That was very fun to work on and to develop. This is the copy of the actual first page of the patent. The actual title is Method and System for Measuring Physical Phenomenon in an Open Water Environment. But when we put this together, we were directed to change the name to this from what we originally had was the WILMA Moored Sensor System. And WILMA stands for Wingo Inline Measurement Apparatus. And Rob Wingo is one of the co-inventors, along with Bill Venetia, Dr. Bill Venetia. We all worked at Carderock at the time. Rob and Bill have now retired, so I'm left to give this presentation. What I wanted to point out here on this slide was the original invention disclosure was submitted in March of 2014. 1 year later, all the paperwork was ready to go to the Patent and Trademark Office in DC, and the patent was issued 2 years after that. So it took a total of 3 years from the time we submitted it until the patent was actually issued. This is a cartoon basically describing what we invented. At the top is a large spherical buoy as syntactic foam, and I'll talk more about that in a minute. But below it, a few feet, is the battery pack to supply power. And since there are sensors, electromagnetic sensors in this buoy, we had to get it away from the batteries, away from it, so as not to cause interference. At the bottom, we have a pinger so we can locate where the anchor landed on the seafloor, acoustic release and a backup acoustic release, plus 2 floats to bring it up to the surface. Now, looking up at the what's inside this buoy, sensor buoy, we have electric field sensors, which are basically the same type of little electrode that they put in EKG tags that the medical profession uses, but it's the same thing. And there are 6 of them on this sphere. And what we do is we have a very low noise amplifier that's connected to 2 of these electrodes, and we measure the potential difference between them. And we have a pair at 45 degrees, one at -45, and one forward and aft in the horizontal direction. It goes into this electronic unit that's inside the ball. It has very low noise amplifiers. It has a triaxial flux gate magnetometer, some what do you call it? Positioning type equipment, orientation sensors, and some other stuff, some acoustic modems and things like that. The way this works is that if this sphere wasn't there and the electrodes were just on the end of, say, two long insulated poles, you measure the potential difference between them. And really what you're doing is you're measuring the voltage drop of the electric current flowing through the seawater. Because they're mounted on this insulated buoy, insulated sphere, the current has to go around the sphere to get to the other side. So it has to go a little bit further distance, which increases the sensitivity of the buoy. And if you work out the mathematics, these electrodes are equivalent to being 2 meters apart instead of 1.3 meters. One of the problems you have with a moored electric field sensor is if it moves through the Earth's magnetic field, the leads on these sensors will have voltage induced in them. And since they're trying to make sensitive measurements, you can't tolerate too much movement. If you look at the physics of it, rotating the ball on its axis does not produce noise. It's the linear motion. So if this ball moves back and forth in the water column, it will produce electric noise. So we wanted to keep this sphere as stable as possible. That's why it's so large. We have a lot of buoyancy and a heavy cable anchor at the bottom to try to keep it from leaning over. It's a pretty big size, isn't it? I'm talking about the buoy, not Rob. The buoy is so big that you really can't put it in a tank to calibrate it. So the way we had to calibrate it was to actually deploy it and use what we call a calibrated source, artificially generating an electric dipole and trying to determine if the measurement agrees with what theory says it should be. And that way we can tell that it is reading what we expect. Now, these are the electric field electrodes. There's one there, and there's one on the opposite side, right across from it, the forward one and the aft one. And then there's one down here and one up here. So it makes a 3-axis electric field sensor. And if you take the vector sum of the 3 components, you end up with a total electric field, which is what we're interested in. This is a photograph of the calibrated source that we use to calibrate the sensors. It's really a long PVC pipe with copper electrodes on each end and a cable that runs between them, a power supply that's run by these batteries. It has a roll pitch and heading sensor, underwater tracking pinger, a pressure sensor for depth, and a fiber optic multiplexer that allows us to control how much current we want to come out and to send some of the onboard measurements back to the towboat. We could put, typically, we would use about 20 amps in this source. So the effective dipole moment for this is 100 amp meters. It's a comparison of what the actual measurement from that buoy when the calibrated source was towed past it, compared to theoretically what it should be. As I said, the source strength is 100 amp meters. It was towed 25 meters off to the side of the buoy. The source was submerged 58 meters and the actual sensor buoy was 82 meters. So it's about another 24 meters deeper. The water depth where the anchor was 162 meters, and the water conductivity where we deployed this was 5.3 Siemens per meter. Now you can sort of see what the noise level is. If you come out here where the signal has disappeared, the noise is under 3 microvolts per meter, which is very, very good for a moored sensor. Some of the highlights of the Wilma sensor program. The impetus for developing this was to satisfy a congressionally mandated requirement that we were not going to be able to meet any other way. And so there was a very urgent need for this, and we came up with an idea on how we could satisfy the congressional mandate in the limited time that we had. This unit was designed, constructed, and calibrated in the water, and it only took 6 months. It's now routinely used and deployed at sea. In fact, we've already used it twice this year in 2021. And we've had it anchored in water depths over 5,000 feet. Actually, I think it was 5,500 feet in AUTEC. And the development team who put this together received the NSWC Teaming Award. And Rob Wingo, who managed this, received the Captain Harold E. Saunders Award for exemplary technical management of the Wilma moored system. We have a couple different variations of this, different types of sensors internal, and this one is Wilma, and we also have one that's called Fred, one that's called Dino, and one that's called Bam Bam. And that's basically all I have. Thank you.
Dave, are you there?
I am. I thought you were going to introduce Trish, but I'm happy to do that. So up next, we got Trish Shields, who's going to provide a prep to our main event for the day, Dr. Craig Lawrence. So Trish Shields is currently serving in a detail position in Carderock's front office, focusing on digital transformation, digital strategy, of which machine learning, artificial intelligence are part of that. And I will hand it off to Trish to kind of give us some opening things to think about before we hear from Dr. Lawrence.
Thanks, Dave. Afternoon, everyone. So as Dave mentioned, we are putting together a digital strategy for Carderock in order to transform the processes that we use to get the product out and complete our mission. And AI and ML, artificial intelligence and machine learning, are very key technologies and capabilities that we're looking at and working on employing at Carderock. And that's not just Carderock alone, but also the DoD and the Navy as well. And what I would say to that is, up until fairly recently, the public perception of artificial intelligence and machine learning has been heavily influenced by the portrayals in popular culture science fiction. And let's be honest, those portrayals are not necessarily showing AI and ML in a favorable light. It's usually a rogue robot or machine that's deciding what's best for humanity, and things roll downhill very fast from there. And so that perception is going to influence the way that the public and also our sailors and warfighters start to employ and gain trust in the systems that we're developing and using. And so, the reality is the future is less likely to be machines operating on their own, and more likely that they're going to be some form of human-machine teaming. And you can see that right now in the apps that you have on your phone, and they have some sort of recommendation systems to them. So Netflix, in the way it gives you recommendations on movies, and Google Maps on routes and things of that nature. And those human-machine teams are predicated on trust. And so for Carderock specifically, we're trying to employ AI and ML into the way, not only the things we produce, but also the way we produce them and the way we operate. So it might be something like building an AI ML system into our set-based design tools to have it generate and display a recommendation for a design with very minimal human interaction during the analysis. Or it could be something like employing a bot and natural language processing to assist in the generation of contracting packages and to reduce the time and error in those packages. So how do we know an algorithm or model that we design is going to work? And how do we translate uncertainty from an algorithm and the analysis into something that an end user will understand to help build that trust between the human and the machine itself. So our keynote speaker, Dr. Lawrence, his presentation today is gonna help us understand how to start to address that. And so Craig Lawrence is the Director of Systems Research at the University of Maryland's Applied Research Laboratory for Intelligence and Security, ARLIS, and that is a university-affiliated research center, UARC. At ARLIS, Craig leads a group focused on operationalizing artificial intelligence, autonomy, and augmentation technologies. Prior to joining ARLIS in 2019, Craig was a program manager at DARPA in the Strategic Technology Office, where he managed the battle management command and control portfolio in support of the Strategic Technology Office's Mosaic Warfare Strategy. Prior to joining DARPA, Craig spent 15 years in industry, culminating at BAE Systems, where he managed a group focused on defense and intelligence community research and development. And so with that, I will turn it over to Dr. Lawrence.
Thanks, Trish. I will go ahead and share the screen. Okay. Thanks for the intro, and thanks a lot for inviting me. This is a great opportunity to talk to folks about an area that's really, full disclosure, this is new ground for us as well. Well, first off, we're a new UARC. I'm sure probably most people on the line are thinking, what? There's a UARC at the University of Maryland? There is. It was chartered in 2018. It's actually a follow-on from a predecessor UARC that was at Maryland that was NSA funded and focused on languages. And we moved sponsorship in 2018, just before I joined, and now fall under the Undersecretary of Defense for Intelligence and Security, and our charter expanded greatly. And if there's time at the end, I'll tell you a little bit more about ARLIS. I've got a little bit of a shameless plug at the end or in the slides if we don't get to it, and folks are interested in learning a little bit about more about who we are. As Trish mentioned, my specific mission area within ARLIS is I'm very interested in what I'll call operationalizing these technologies, AI, autonomy, augmentation. And what I mean by operationalizing is passing through that valley of death, as we would call it at DARPA, is getting from the late stage R&D, say 6.3 type development, actually into the hands of operators and warfighters. And there are many challenges associated with that, and especially with these technologies. But one of them, and I think one of the key challenges is trust. Once we get it in the hands of the operators, they didn't necessarily always trust the technologies, if they didn't understand what was under the hood. And so got to thinking about that more and more. And my role here at ARLIS is in trying to figure out ways that we can help. So we're a trusted agent as a UARC. So we're not doing as much of the development of the technologies. We're helping the government understand, our government sponsors understand how they can better incorporate these technologies. Lots of issues beyond just trust. There's a lot with human machine teaming, human computer interaction, a lot with test and evaluation. But trust is kind of at the heart of all of it. It's how do we get the users and operators to trust these tools? Now, I again, disclosure, I'm a technologist. So my background was actually developing these tools for many years, tools that are focused mostly in battle management, command and control world. And then at DARPA, I was focused on battle management, command and control. And it was less about, so it was the hardcore, the algorithms, developing the systems, integrating systems. And I have to admit, I didn't think as much about things like trust. And I think that, looking back, that hurts us. That hurt us some in terms of actually transitioning these tools. And that's why I've made it a new mission of mine here at ARLIS. And so I'll tell you a little bit in today's talk about what we're thinking about in that area. All right, so I'll start with a little bit of an overview. Trust is, we need to spend a little time thinking about how to define it because it's something that you know it when you feel it, but how do you actually define it and quantify it and measure it and model it? That's a different matter. And then we'll talk a little bit about, well, why is it hard? What are the specific challenges with trust, with AI and autonomy technologies? And then I'll pivot to talking about some approaches that folks are exploring to developing trust. And some of them are more constructive design time. What can we do as we're developing a system to make it more trustworthy? And then some of them are how can we then then the latter half, what I'll probably spend most of the time talking on, and what we're focused on here at Arliss, is the test and evaluation piece. How can I establish trustworthiness and do it in a way that I provide evidence that the system should be trusted, and then helps users and operators trust it? So some assessment. And as I mentioned at the end, if there's some time, I'll give a little shameless plug, our overview of Arliss, for folks that are curious about who we are, where we are, what we do. All right, let's go ahead and dive in. So trust overview, and as I say, I'm an engineer, technologist, and learning about these, as I start to build this mission area. But you deeper questions about trust, one of the nice things about Arliss is coming out of what we did with NSA and language and cultural focus, we have a lot of cognitive psychologists, which is kind of unique. Cognitive psychologists, anthropologists, it's not just all engineers and technologists. So I'm getting a lot of help from them in understanding some of these issues. And we do have some native expertise, even though we're kind of new. So there's some definitions. First, we all kind of know trust, and we know when we feel like we trust something. But let's try to look at some of the specific definitions. And so first off, from the dictionary, just look it up. It's the first bullet here. Firm belief in the reliability, the truth, ability, or strength of someone or something. So belief in reliability, abilities. Then looking at the trust literature as applied to AI and autonomy, I think we start to narrow it down a little bit into things that maybe are a little bit more useful for what we want to do here. So a couple of definitions I liked as I went through the literature is Leoncy in 2004, the attitude that an agent will help achieve an individual's goal in a situation characterized by uncertainty and vulnerability. And that's important. So there's a goal. So I, as an operator, have a goal, and I understand that the situation I'm in is uncertain, or it might be risky or vulnerable. Trust is if I trust that system, then I believe that it'll help me achieve that goal, even amidst the uncertainty and vulnerability. Similar, the next definition, trust is the human's confidence in the reliability of the system's conclusions and its ability to perform specified tasks and accomplish defined goals. So that's more of a reliability based. I think it'll always give me the right conclusions. And I think I know that it'll perform the task and accomplish the goals, as long as it's within the bounds of what the system's designed to do. I think implicit in that is still some of the things about uncertainty and vulnerability that were in the previous definition, but it isn't explicit. And I kind of like the last, being an engineer, I kind of like, mathematician, I kind of like the last definition because it puts it more in, system-y terms. Co and so, and I rely on them for a couple other definitions later. Talk about it as a multidimensional latent variable. So multidimensional, it's multifaceted. It's not just one number. It's latent, so it's not something we can directly measure. It's hidden, but it somehow mediates the relationship between the events that have happened in the past and the former agent's subsequent choice of relying on the latter. So the human's agent, it's their belief, their choice, of relying on, say, the AI or autonomy in, again, an uncertain environment. So I like that. It's sort of trying to make it a little more formal and related to things, events that have happened in the past, and whether or not I will rely on that agent in an uncertain future. So a few definitions. Also from the same work, I think this is important also to distinguish. When you think about trust, it's easy to immediately think of trust and trustworthiness as the same, but they're not. I think you could think of trustworthiness as something that is a property of the system. It's really how trustworthy is it? As it performs, how much should you trust it in a sense? Is it something that should be relied on in the environments for which it's intended? So as things are happening, you're demonstrating. The bottom graph is events are happening, it's demonstrating through maybe performance that it's trustworthy. So it's actually giving you evidence that it specifically should be trusted. Whereas the trust is what's the human's perception then of as time goes on and I'm seeing the performance, how does my trust, that latent variable, again, how does that grow in the system? And there can be a mismatch, and this is important. If there's a mismatch, you could have it in one direction where you're over trusting, that's bad. Or in the other direction, if you're trusting more, then it's trustworthiness, that's overtrust. On the other hand, if you don't trust, if the human doesn't trust the system to the extent that it should be, it's trustworthiness, well, then you get undertrust and you get underutilization then of a system. So underutilization there, where maybe you're using the system in a situation where you shouldn't in the case of overtrust. And so those are important distinctions. Right. And related to that, you'll often hear it referred to as the trust gap versus the automation bias. And so I think a good way of thinking of the trust gap is it's an inability to trust machines to do the work of people. You just don't think machines should be doing whatever the specific task is. And again, this is the undertrust before, and your unwillingness to deploy or properly use that system. And one example from the literature is that surveyed ground tactical air controllers, GTACs, and the general feeling amongst GTACs is that they would much prefer using a manned platform for actually releasing munitions or tactical air controllers over an unmanned, even though an unmanned system could perfectly well do the job as launching a weapon. Whereas automation bias, on the other hand, is trusting too much, basically. The delegation of judgment to a machine when maybe you shouldn't always. And a failure to question the algorithms if they make mistakes. And so there's been some high profile examples of that, of course, with some airplane crashes recently, commercial airline crashes. There's an example of 2 of the Patriot missile fratricide against the F-18s. And this is also related to another thing. I don't have a slide on it specifically. Micah Ensley, who does a lot of work in human machine teaming and was with the Air Force, chief scientist for the Air Force for a while, calls the automation conundrum. And this is where it's, again, it's the point where as systems become more and more automated, the human operators are less and less aware of the situation and are unable to act. Like I think that's the case of, say, some of the commercial airline crashes, because they are ceding control to the automated system, and they're then losing situation awareness. And then when something does happen, they're unable to actually respond in an appropriate manner. So that's often referred to as the automation conundrum. Okay. So categories of trust, this goes back to, and I put one specific reference down here, but these categories actually come up a lot in the literature and other in other references you'll see.
Hey, Craig?
Yes.
Let's apologize. So we've gotten a question that came in on your previous slide, and I just wanted to make sure you had an opportunity to kind of touch on it while you're at that point in your talk here.
Oh,
so the question was, do you have any thoughts or comments on the Uber self-driving car that killed a woman because, it didn't, if I remember correctly, it was only trained to identify pedestrians when there's a crosswalk, and there's no crosswalk, so therefore it just kind of plowed through. So I'm kind of curious if you could talk the trust gap.
I don't know as much about that one. I know that another case was when the Tesla crashed into there was a white truck that crossed in front of it. And that was absolutely a case of overtrust and in fact misuse of the system. My understanding was you were only there was, well, fairly clear, supposedly, guidance that you're only supposed to use that system, that automated driving system, on roads with no crossroads. So that, they hadn't fully vetted it for the case where you could have traffic crossing. And the person in that case was using it on a road that had plenty of intersections and didn't follow so we're over trusting and using it outside of the bounds of where it was supposed to be employed. And unfortunately, I don't know all the details of the pedestrian one, but I imagine it may have been a similar case, but maybe not. I can certainly look into it. And please do, I don't see the Q&A the way I have my screen set up. So yeah, please do feel free to jump in if I'm missing a question. That's relevant.
Yeah, no worries. All right, back to you.
Yep. So I mentioned there's categories of trust, and these are fairly common throughout the literature. I pointed to one reference that I think is a good new recent paper. So there's dispositional trust. That's the tendency of a human to trust AI and automation, their inherent tendency. So sort of their built-in disposition towards trust. Not much we can do about that. They come in with their own biases. Then there's situational, So there's the attitude towards the AI or automation is influenced by the context. So their current mental state, I said mental state, I meant state, the environment. And this, this maybe we can do something about by controlling how much AI or automation is employed given the environment. So if you recognize the situation and have some sort of model of trust, you might be able to adapt. And then there's learned trust. So there's the attitude towards AI and automation based on past experiences. So this is something that evolves over time. It's dynamic. And this is something certainly we have a lot more control over. If the technology is being used appropriately and doing the right things, people will gain trust. Unfortunately, what we do see is that once something goes wrong, the technology makes mistakes, it's highly nonlinear. People then very quickly lose the trust. And so that's something we have to be mindful of. All right. So measuring trust. So kind of got a feeling for what we mean by trust and the categories of trust, but it sure would be nice if we could actually measure it. And that would be good from many perspectives. It would be good, certainly from a test and evaluation perspective. We want to understand how much operators trust the various systems before we deploy them, but also, dynamically in real time, we'd like to perhaps have a system that can be measuring trust on an operator and adjust some sort of operational parameters, maybe the level of autonomy or the level of control. And so you can see there's many reasons why it'd be a good thing to be able to monitor. Unfortunately, it's difficult. As I mentioned before, it's a latent variable. It's hidden. There are some observables. It's maybe partially observable, not fully observable. So there have been several attempts in the past. Unfortunately, some of the early ones are basically self-reporting. Stop, do a quick survey, very subjective, get back to it. That's not super helpful. That's very disruptive, and it's not something folks want to do. I'm not up to date on the latest here, but there are some attempts at being a little more objective. Some physiological measures that you might use can be less disruptive if you can do that. Can be done in real time. There's some indications apparently from eye tracking you can get from trust and other skin response, galvanic skin response, maybe the audio of the way the operator is interacting with the system, other social cues that you might get if you're monitoring the operator. So there's research being done on ways we might, physiological measures we might use to measure trust too. Issues, of course, with many of these approaches is they're hard to validate. And how do you validate when you don't really know truth for the trust, but maybe you can get it through confirmatory testing, whether that's other modes of physiological measures or self-reporting, comparing to a survey. There's not a lot of that right now. And there's some measurement invariance reliability that hasn't been demonstrated that, from one method to another, the measurement invariance that we get the same types of response and it's reliable. So it's a new area and there's still a lot of work to be done. And then maybe the last thing I'll say on trust before we get into the specific trust with AI and autonomy is it would be nice to model trust. There's a lot of good reasons why we'd like to model it. So we might want to do this to predict, in real time when we're getting to a situation where trust might be an issue. So we might want to adjust the parameters of the system. There's a number of good reasons why you might want to do that, and maybe you want to model before you even deploy too. You might want to model given for a certain application, is this likely to be trusted for a certain class of users? So there's been some attempts at doing that, at modeling it. There's a fairly rich literature on folks trying to use probabilistic graphical models to try to understand all the things that trust depends on and model how trust might evolve. There is some work where folks have tried to put it into a partially observable Markov decision problem. There's more recent where they're trying to really get deeper at a theory of mind and understand what makes trust, what makes folks trust a technology or not trust a technology. And so you can imagine there's the influences in the little diagram on the right that are prior, that are sort of, as I mentioned before, the the dispositional, your inherent trust, then some situational things, and then what you've learned from the past and your pre-existing knowledge, and that goes into your maybe level of trust before you actually start interacting. And then there's the dynamic piece where you're online, things are happening, you're performing well or not, and trust will adapt. All right. Okay. So now for the next section. So now maybe we've got our head a little bit around what trust is and what we might do with it. Now I'd like to spend just a little bit of time talking about some of the challenges associated with, so why is it a challenge for folks to trust AI and autonomy, and why is it a challenge to establish trust and with these specific technologies?
So I got a question for you before you move on there.
Yep.
Just kind of curious, got a question around whether, how might you differentiate complacency from trust? So is that something that you have to kind of think about specifically when you're factoring into the trust model? I mean, it's just like you get those edge cases may come back and bite you.
Yeah, that's a good question. Craig, not a psychologist, but my personal feeling is complacency feels a little bit more like the overtrust. I'm just going to let the technology do its thing. I'm sure it'll be fine, and you'll get the same sort of issues. Now, I wonder if it would be measured differently and modeled differently, though. Complacency, I think it may have the same effect, but it's a good question. I'm not sure what the implications are for the latter stuff I was talking about, the sensing and modeling. Question.
Great, thank you.
Okay, so I'm going to start with definitions. There's no shortage of definitions for what is AI, but just so we scope things a little bit. You can pick your favorite recent strategy document or report that's come out, and there's good ones out there, and they have various definitions that are basically the same. Things like, AI is what enables computers and other automated systems to perform tasks that have historically required human cognition, and that we typically consider human decision making. Or maybe AI is the ability of the computer system to solve problems and perform tasks that require human intelligence. So those are very consistent. The academic community, the last one, the AAAI community roadmap for AI, they published, I guess it's been a year or two ago now, just thinks of it in a little bit different spin. It's about synthesizing intelligence. And an AI system is a computer system that exhibits some intelligent behavior. So while those make intuitive sense, I think, for artificial intelligence, it's still a little bit abstract. So what I like to do is I just took the table of contents from the classic AI textbook, Russell and Norvig, and I think there's even a more recent edition now, a fourth edition, but it probably has roughly the same table of contents. And so look at, well, what are the technologies? When we say AI, what are the specific technologies? And first off, the one thing I like to point out to folks, because everybody's so impressed, and rightly so, by all the great results recently with machine learning and deep learning, and they tend to equate AI with those learning technologies. But that's really, in the broad field of AI, that's just one little small piece. It's a very successful piece right now, and there's a lot of work going on there, but it's much bigger than that. AI includes everything from problem solving through search methods, classical search, or more sophisticated search. It includes knowledge-based approaches that were, you go back to the 80s and 90s, so logic-based approaches and classical planning that were at the forefront of AI technology, and then incorporating uncertainty into that. So then you get into probabilistic models, partially observable Markov decision problems. They all actually fall into these categories. So AI covers a broad class of technologies, and I just want to point out that it's more than just learning, and it's really, any of these decision-making, reasoning, knowledge representation technologies. And then I think of autonomous systems as systems that are enabled by AI. And again, I mean AI in that broader sense of all those technologies I talked about on the last slide, where you throw in, some important elements of autonomy are situated agency, so it needs to sense the environment, assess the situation, needs to build a world model, essentially, in order to enable it to make decisions. It needs to be adaptive, using modes of thinking from very low-level rules, so think control theory, just very low-level actuation, all the way to higher-level reasoning about how to achieve goals. And then there's new challenges when you throw in things like multi-agent emergence. So what happens when you start interacting with other agents? Maybe those agents are humans, by the way. It's not necessarily more robots, so to speak. And then a real wrinkle is that these autonomous systems may learn new behaviors over time and with experience. So as they're experiencing the world, learning the world, their behaviors could change in a non-deterministic way. And then the desired properties you want out of an autonomous system, trustworthiness, of course, that's the topic of today's talk, but you want them to be proficient in the tasks that they're doing, and you want them to be flexible, which is where the AI comes in, so they can flexibly confront new situations, new environments, etc. So definitions. Okay, so what are some of the trust issues then with systems like that I've just described, AI and autonomy? Why wouldn't people trust them? Well, I think it's not a surprise. I think most people are familiar that they tend, AI systems and learning systems, broader AI systems too, but learning in particular, it's fairly famous that they're somewhat brittle. They can't reliably handle uncertain or new situations. They're vulnerable to adversarial attacks. An autonomous system, robotic system of any kind, if they do have a malfunction, or they fail, or they're misused, that can lead to unacceptable levels of damage. And so there's trust issues with that. It's certainly well known. There's fairness and bias issues. Earlier, Trish mentioned, the ethics principles. That's a big concern. Fairness and bias within AI. And really, one of the big issues is with the machine learning approach, and to some extent some of the other approaches, is the lack of explainability. It's very difficult to look inside of an AI-based algorithm in many cases and get a clear explanation of why it came to the decision it came to. They're somewhat opaque, though there's been certainly efforts to fix that. They still remain to be somewhat opaque. And what I'm most interested here, and what my focus has been on, because we're doing less of you can think of the first 5 bullets here is more about things you need to deal with while you're developing, things that you could fix through development. And then the last is, well, in order to give sort of certificates that enable operators and users to have some trust going in that the system will work as they expect. That requires test and evaluation, and there's all kinds of challenges with test and evaluation of AI-based and autonomous systems. They help you, so T&E helps you characterize the issues above, and lets you sort of characterize, again, how brittle they are, what environments they work well in, whether there's a bias issue perhaps, or a fairness issue. But really, T&E provides what I believe to be that basis for trust in and of itself. You build an assurance case that says, yes, this is a system that you can trust will behave as you expect it to within these conditions, under these assumptions, within certain conditions. Okay. So why is it hard to do T&E for AI and machine learning? I mentioned I mentioned the brittleness issues. Well, we want to test for that. And so, but testing for all possible scenarios with all possible inputs just simply isn't possible. A lot of possibles in that sense. It's hard to cover all the cases that you're going to interact with in the real world. It takes a lot of data if it's a machine learning approach. This particular, the bullets I pulled here from this report was very much focused on the machine learning part of AI, just as an example of what some of the challenges are. There's system level issues too, which a lot of people don't think about. When you plug in a machine learning or AI-based algorithm into a system, you have to think about how it interacts with the rest of the subsystems. And often failure can come from unexpected interactions between systems and not just failure of the AI itself. And then I mentioned an important part of T&E is traceability and interpretability. And those algorithms that aren't explainable create all kinds of challenges for that. And then you throw a human in the loop, and that makes it even harder. Autonomy, makes it expands the space of why it's challenging. There's absolutely the state space explosion. So if you think of traditional T&E for software systems, where you want to explore all potential states, or even for physical systems, you can't do that in a non-deterministic autonomous system where you can't exhaustively search or examine all the potential states it'll ever visit. The environments that it'll be operated in are unknown, unpredictable. You just can't test all conditions. And assuring correct behavior in the countless number of environmental conditions is just not possible. There's a concern of emergent behavior and interactions between systems. Again, this is a system of systems issue, potentially unintended consequences. So there's certainly overlap here with what we were talking about in the last slide. And then there's that human-machine element. It's human-machine interaction. It's critical to trust, and explainability, transparency are critical parts to trust. And so we need these methods to help ensure trust through test evaluation, verification, and validation, in order to give that assurance to the human that this is a system they can use within the conditions that they're intended to be used. Okay, so now I'm going to spend some time talking about some approaches that I've seen. That are much of it is current work, in progress work for building in trust to these systems, and then for assessing trustworthiness through test and evaluation.
So a quick question for you before we move on to the approaches, and if you're going to get to it, great. But as you're talking about brittleness. With a question on complacency versus trust, I think of at least for a machine learning or a regression type algorithm, it's very clear to me that you have scenarios where the answer is clearly an interpolation scheme where you're pulling something where you have some representation of how you expect the system to respond versus an extrapolation. And I wonder how much you think the self-awareness of the request for an answer of a system back to those inputs and where how far outside of those limits you might be is a way to for that system to kind of self-report its own awareness of uncertainty or trust back to the end user.
Yeah, I think that's a great idea. It's certainly being aware of the operating environment, the operating envelope, so to speak, and using that loosely for whatever application you're talking about that you're supposed to be operating in, or say if it's a machine learning image classification, maybe there's certain lighting conditions that it's certified to work well within these conditions. When you go outside of that, maybe not so much. I think that would be an important element of trust if the system did self-report that, okay, I'll give you an answer, but it's outside of my typical operating conditions, so take it with a grain of salt. Is that what you're getting at?
Yeah, it was. It was that way of saying, hey, I'll give you an answer, but I wouldn't give a lot of faith in it or proceed carefully, and then the human can do the integration of what the impact of that decision is and whether they want to follow the recommendation.
Yeah,
thanks.
That's a great idea. Yep. All right. So I mentioned before, I split things up into two broad areas of developing trust in these systems. There's building in trust, and then there's assessing trustworthiness through test and evaluation to give you a certificate that you can trust the system, so to speak. So building in trust, there's a number of approaches that folks are looking at, and I think they're all important. And many of them, there's some overlap here, and of course, but let's walk through them. So first off, transparency. I think it's generally recognized that if the human operator understands, has a better, deeper understanding of what this system is doing, what it's trying to do, and for an autonomous system, that might mean exposing the goals, the high-level goals that the system is currently working with. What are the beliefs right now related to the world model? What does it think about the world right now? Maybe what's its intent? So a subset of the goal would be the intent for what's my next move, essentially. And so understanding the state and the world model. So just having a better sense of what does my system currently know, think about the world, and what does it currently think it should be doing about it? That's transparency. Of course, explainability. We already talked about the challenges of that, but just the ability of a system to explain its rationale and whether making a classification or making a decision. How did you come to that? If you could do that, I think that would build in a great deal of trust. And then there's auditability and traceability. So auditability would be in development but also in execution. So in terms of how the technology was developed, where the developers transparent about the methodologies, the design procedures, their methodologies for developing the system, the data sources they use to train it, and the limitations on those data sources maybe. So all having a good audit trail for all of those elements of developing the system, and being easy to trace back, and then maybe logging during execution, so you can look back and see areas where it didn't work as well or worked better, and just being able to have a deeper understanding of that would help towards trust. Reliability, of course, that obviously, if it performs well over time, if it performs its intended function adequately over an extended period of time, you're going to build trust then. So if it just, it's obvious. Robustness, that's how well do you operate in adverse conditions. And this could mean many things. This could mean, adverse environmental conditions, or, changes in op tempo, or it could mean under adversarial conditions. So maybe in a machine learning example, how robust are you to adversarial examples when you're given images that are intended perhaps to fool the classifier. And then responsiveness, how responsive can you be to the environment as the environment changes, and the users. So you'll have different classes of users with different levels of training. Do you adapt? Does the system adapt as expected? I'm going to do a little bit of a deep dive into some current work that's being done in a couple of these areas. So I'm sure many of you heard of the DARPA's Explainable AI program, where the whole idea there was very much focused on machine learning, specifically within AI. And because that is one of the hardest, that is where, as successful as it's been, it's also been the hardest nut to crack in terms of explainability. And then the other traditional AI approaches, thinking back to that outline I showed you from Russell and Norvig, a lot of planning approaches, it's kind of easy to tease out an explanation, or even optimization approaches. In many cases, it's easy to get an explanation, but it's harder with machine learning and neural nets in general, or deep learning. And so the goal of the program there was to develop new ways of modeling and creating what are called explainable models, and then interfaces for users basically to query and understand. Understand why it came to a decision it did, why it didn't, understand, back to the earlier question, the conditions under which it succeeds and which it fails, and so when the system should be trusted, when the machine learning system should be trusted, and ultimately when it makes mistakes, why did it make mistakes? So it's really targeted at users that are depending on decisions and recommendations of the system, and needs to understand that rationale, just can't blindly accept it and act on it. And so there was several prongs to the program. They wanted to look deeply at how to make new models that are explainable. And then there was an interface component to the program as well. How can they provide those explanations and give the user a tool to query, and then convey how maybe to correct those mistakes if they get to that. They say perhaps. This was from the industry day. Robustness, there's a number of programs going on that are looking at robustness. Again, this is a machine learning example because it's, there's been a lot of famous cases of seemingly minor perturbations to an image that cause wildly wrong classifications. So if you look at the left, there's the competition every year how well the best algorithms are doing against the ImageNet. And it seems like it's a game, a cat and mouse game, where a great new classifier comes out, and then within the year, some adversarial method, deception method comes out that just destroys their performance for that. And then they come up with an approach to defeat that adversarial method, but then a new method comes out, and it's back and forth. And so the point of the GARD program was to look at take a deeper, more fundamental look at a generalization of robustness. So instead of just defeating a specific attack, is there a way that we can make classifiers more generally robust, so that they'll respond well, and as we get better and better, to any attack, that any adversarial type attack. And so they've been working on that. It's an ongoing program, and they're building test beds as well to test this out. Okay. So that's again, these are some techniques for building in trust. If I know that the last one is explainability, so that's building it in so that I can understand the solution and trust it better. And then robustness, so I know I can trust that even if I'm getting some deceptive attack, that I could still potentially trust the answer that I'm getting out of the system. Finally, there's a whole new movement. Ben Shneiderman, who was a distinguished professor here at the University of Maryland, he's working on, he's a pioneer in human-computer interaction, and he's always been a human-first kind of guy. He's not, AI is nice, but it really should be human-centered AI, and it should all be about the person and amplifying, augmenting, enhancing, and empowering them. And so it's a whole new, he's got a series of papers out. There's a link there to one. We ran a workshop back in January, and he spoke on it. I took a slide from this, and he's writing a book right now called Human-Centered AI. And it's a work in progress. The actual processes that he's recommending for how you develop, but it is all about developing systems from scratch with the human at the center, and developing tools. And he points to a lot of commercial examples now, things like the iPhone and several other that are more human-centered and are tools for humans, and that folks trust. So he thinks that trust comes naturally from this approach of design. Okay.
So I had just a quick question, and I think this is a great place to ask it. So
Yeah.
One, just first a comment, as my kids get older, I'm trying to teach them, not to blindly rely on the output of, say, a GPS,
Right.
but to take that into context. I think there's a great example here, but I'm kind of curious, a lot of the stuff you've talked about as engineers developing systems that might get deployed into operational usage.
Yeah.
There are things that we use to interact with that system to understand it that may or may not make sense to 18 to 24-year-old sailor on a ship.
Yeah.
Or Marine out in the field. And so how might you look to kind of not only address trust to the developer, but trust to the end user in terms of that human machine interface and relationship there in a way that kind of addresses both those?
Yeah, no, and you're right, there are two different things. So a lot of what I'm looking at with the testing, the developmental and operational test, is more focused on the developers and helping them understand whether or not this is something they can trust. But the trust for the operators and helping give them whatever indicators they need to be more trusting. I think it's still in those same categories that we talked about. There's still some level of explainability and understanding the rationale for making decisions, but it's got to be in a different language. It's got to be in a language that they understand and makes sense in their context. And I think a lot of what Ben is pushing here in the human-centered AI, it was a good place probably to bring up this question, is thinking with the person first, the user first, and then building the tools that just help them do their job in a way that they understand. So I think my feeling is it's the same things with explainability and the robustness is important, of course. Same things are important from their perspective, but you have to do it in a language, or there's a display element to it. How do you display this? How do you display the situation in terms that they'll understand and not technical terms? And they're different from what the developer wants. So it's not that wasn't a crystal clear answer, but I do recognize that there is a difference, and you have to factor that in as well for the deployed systems.
Yeah, great. No, appreciate it. I had some other questions, but I'll pause there. I'll just say that the question came in as you were chatting, and a question about the application of output of machine learning models or AI in terms of mixed reality, augmented reality. And I'm assuming again that just kind of falls within that human-centered AI in this sense of how you display the results back to an end user. And that might be a way too to get trust to the operator, because if they had a a display that showed the result in situ with what they're seeing, then they
Right.
could have that embedded trust that
Yeah.
they're believing what they're seeing recommendation.
Yeah, I totally agree with that. And it is something that it's a strength here at the University of Maryland. There's a lot of competency in AR, VR. I'm glad you brought that up. And it's something we've dabbled with a little bit. I did some work last year for the Army in distributed planning using AR or VR, actually, distributed command posts. We're still struggling to find a killer app for that. It's hard to get a lot of adoption on those technologies, but it could be there. Maybe that is something we should be looking at. Is maybe it gives you a richer interface to sort of explore some of these explainability issues. I haven't specifically looked at that, but it seems like potentially a good application.
Okay.
Is there another question before I press?
There is. So someone was asking if there's typical defined threshold in trust models to distinguish between an AI human might see as trustworthy or untrustworthy, and then the question becomes is if that becomes situational.
Yeah.
How do you change that threshold in the sense of like I'm in A environment or B environment or C environment? Now I gotta be smart enough to figure it out. I think it's related back to that interpolation, extrapolation type discussion we had earlier.
I totally agree. But I think it's a great question because that is what you have to do, especially, things like it has to be dynamic because there are certain environments, where it isn't just static. All environments you should trust at the same amount. You need to understand when you're in a new, I can't give a crisp, precise answer to that because it's an it depends on what is the application you're talking about, or are lives at risk, or is it maybe more of a back office thing, or what's the environment, what phase of war are we in, if it's an actual weapon system, for example. But you're right on in the point you're making about the interpolation and recognizing the environment and how I think the hard question there is I guess. First off, we talked about the challenges of measuring trust and then understanding what they're setting those thresholds. So it's a good question that I don't have the answer for yet, but it's something that's very important and I think ought to be looked at carefully, is understanding where those thresholds are to whatever it is you're switching, whether it's the level of automation or and maybe becoming more automated in certain conditions, or same way back off, you really shouldn't trust the AI in this area. We're not trained for this. That'll all be situation dependent. Good question.
All right, we got another question here, but I'm gonna let you proceed because you might address it, and then maybe the next convenient stopping point we'll bring it up. So back to you.
Okay, no worries. So I'm not going to switch to test and evaluation, where I see this as how we establish trustworthiness, which then goes into again some evidence to predispose the users to trust the system. And this is where I think we're focusing more here at Carlos. So I'm going to start by making a few claims, and these are some claims that we explored, and we had a workshop, a virtual workshop, of course, back in January, where we got a lot of T&E experts together to think through the challenges of test and evaluation for AI, especially operational level test and evaluation. So mission focused, not just rock curves for your favorite classifier. And so we focused it around three general areas. We said there's three claims that we're making about T&E for AI, and you can think of it as sort of mapping to the life cycle. The first is we actually need to think carefully about how we specify requirements. And this gets to the trust issue too, is because it's all about, I asserted earlier that you can't necessarily fully characterize performance. There's going to be risk associated with any level of certification you give. There's going to be environments you haven't tested it in. So again, to the trust issue, how do you characterize what's acceptable risk? What's acceptable risk for me to trust that system? And so and that's got to be part of specifying the requirements. So it's policies too. It's not just requirements. Broadly what risks will be acceptable for weapon systems, for example, and then standards and metrics will follow. And then metrics, we're going to have to think about what are those metrics then and then again, we were focused on operational. So again, mission focus, test and evaluation of these systems, AI on autonomy. And they might be more probabilistic. They might, not be as crisply defined. We have to do it in terms of user and mission relevant terminology. And I think this is going to take a lot of field research to understand what the right metrics are, and it's going to be dependent on the types of system you're developing. And we talked a lot about this at the workshop. And then maintaining the AI context within certified limits. We've been talking about that a lot today in this discussion, is using it in the appropriate environment. Claim 2 was, we said we have to rethink about the actual testing that we do. So it's not, so there was the first claim is how we just define what the requirements are. Then the second claim is, so now we built the system and we're testing it. So what are the tools that we use for testing these, where we can no longer, you follow traditional approaches where we'll fully test, every potential environment that you'll be in, every state that you might visit. And we're talking about mission focused again in this workshop. And this is what's important. The reason I'm harping on it is because I think mission focus is where you get to trust. Do the operators trust the system to do the mission that they're charged with doing? And so now you need to think of broader than just testing the system. You need to think about testing it, doing the mission with the users, with the people, before you can certify it. And so what are the tools that help you do that? What are the approaches? And this could be everything from wargaming, we talked a lot about, and simulation, various types of experimentation. And I'll talk a little bit later, sort of towards the end, of building assurance cases, collection of body of evidence, basically, to give to prove quote unquote prove a sequence of claims that gives you assurances that your system will behave as you expect it to, and you can trust it in a certain set of environments. And the final claim that we explored, and I think is important for AI and autonomy and trusting the system, is that it doesn't stop at deployment. You need full life cycle testing because these systems may adapt, they may learn, they may be applied in new environments, integrated into new broader systems. And so you need to think about how we're going to do continuous, iterative and continuous testing, and how we might leverage data that we collect from the field, do better instrumentation. That was a big theme that we talked about with this workshop, is how do we instrument so that we can understand how well the system is performing during deployment in the field. So these were the claims that we're exploring now for full lifecycle testing, full lifecycle operators, and mission-focused testing of AI and autonomy. So I'll talk just some examples, like I did in the last section, of some work that's being done. A very successful approach for verifying, doing test and evaluation, but specifically verification of software systems, is something called formal verification. And there's a lot of work going on right now, is how can we use this very successful method of essentially forming a proof that if you take this system and operate it under these assumptions about environment and the way it will be used, I will prove to you mathematically that it will meet these. You can trust it. It will meet these requirements and these specifications. So there's a challenge to applying this towards AI and autonomous systems, but there's a lot of work going on to do that. Especially, why is it challenging? Because it's really difficult to model the environment, fully characterize the environment. It's hard to formally specify the algorithms themselves, the AI-based algorithms, and there's a lot of computational challenges as well for doing this on these systems. It doesn't scale well. In other words, there's computational challenges because it gets to be a lot of complexity for AI and autonomous systems in a huge state space in a large environment. But there is some work being done. Some work I'd point to here. Some folks at Berkeley, Sashia et al. that are starting to apply it successfully. And it's just another tool in the toolbox. It's not going to solve all the problems, but it gives you some evidence that your system operating in the environment as characterized under certain assumptions, you can prove that it'll perform as expected and can be trusted. Another thing for trust, important thing for trust, I thought it was important to mention here, maybe it doesn't fit perfectly in this section, but something folks have been looking at a lot in autonomous systems, something called runtime assurance. So you may not be able to fully, and we've talked about this, you may not be able to fully test all conditions for a system and fully give a certification that you can trust that it'll work in all the system complexity is just too high, that it'll work in all environments. What you could do is basically wrap your system in your advanced controller, your AI-based, say, controller, wrap it in a system that's gives you an option to switch to a provably safe controller. So maybe using formal verification methods, you've got a simple controller that is provably safe and can be trusted. And the system then just monitors the environment at runtime and looks for those cases. This is relevant to the discussion we were having earlier about recognizing when you're in an environment that you're no longer certified to be safe in, and you shouldn't trust the autonomy anymore. So switch to that safe controller until you're back into an environment. And this is a very important method, I think, that really will have to be incorporated in autonomous systems in the future as we incorporate more and more AI and sophisticated, more non-deterministic processing. You're going to have to rely on runtime assurance capabilities too to make sure you remain safe. And I'll talk a little bit now about.
So
go ahead. Yeah.
Yeah, so before you get too far into this, I had a couple. So the question that had come up before, I think, is relevant to claim 2. I wanted to make a comment around claim 1 and
Sure.
first. So I guess my first comment was I think, an advantage, at least within the DoD, for those folks who are experienced with DWIA, you get kind of drilled in, the kind of formal DoD definition of risk, which has both a likelihood and a consequence.
Right.
So it seems to me that it should be straightforward for us to think about those use cases, the consequences of being wrong in a given use case, and then, the hard part comes is what's the likelihood out of that system.
Right.
So maybe an arm wavy thing, but it might be one way to kind of help identify the risk and figure out kind of, what level of trust you need in order to kind of certify that system as being being able to be used in an operational context.
Yep.
So the accreditation aspect of B&B. So the question I had was, so on claim 2, so the question that came in was around, is it typical to see a list of assumptions that an AI might provide in order to arrive at an answer? And so as you're talking through claim 2, I'm thinking, as you go through T&E and B&B, I have historically, when we've written reports or done experiments, talked about, hey, here's all the assumptions that we used in getting to the answer. So you have to take those into context. And I'm wondering if you have thoughts about how that might come about during the T&E process to say, especially when you start looking at black box type models that are hard to probe, the question becomes is how might you get those out?
Yeah, well, how you get them out from the what the assumptions were from the developers, or you could also say, well, whatever their assumptions were, I can tell you, here's the range of the operating envelope that I've tested against, and I have these results. And maybe that's more important, actually, because for the operator to understand then down the road that it's been tested in these conditions and it performed in this way. You might have been actually talking about how can we extract the assumptions that the developers made during T&E, or did I misunderstand you?
No, I think the person who asked the question was really asking, can the system itself provide the assumptions that it had? So it's probably not strictly a machine learning thing, but some higher level of reasoning. But that might be, as you pointed out, has had a thought, which will go back to that again, that here are the operating parameters on which I was trained or tested,
right.
The current operating parameters I'm in that now, and that might be just a simple assumption that could be somehow put out there.
Yeah.
But
that's what comes to mind to me immediately. Maybe there's a more sophisticated way to do it that I'm just not aware of, but it's hard for me to imagine a better way than just having it documented from here's the data it was trained against, if it's a machine learning example, and the conditions that were present in that data, and then maybe back it up with here's how it was tested. Those are the best, most reliable, I would think, indicators of assumptions.
Great, thank you.
Sure. Okay, so now I'm going to just talk a little bit about assurance cases. It's something I've been interested in how we can start for autonomous systems, how we can start building these certifications, if you will, that a system will work, and with the built-in built-in claims about what the operating conditions that system is certified to operate well in. So first off, assurance, just definition. I like definitions, just to make sure we're on the same page. It's just a justified measure of confidence. So it's not a proof. It's just a justified measure of confidence that a system will function as intended in its environment of use. We've been talking a lot about that today. An assurance case is then a structured argument that allows you to show that the system is sufficiently dependable and to permit fielding in that defined operational context. So within the assumed operational context. These aren't new. These aren't new to AI on autonomy. There's standards out there for software engineering on building software assurance cases. And I put their definition here in quotes. It's just a top-level claim or set of claims for a property of a system or product, and then the systematic argumentation regarding that claim, as well as the evidence and explicit assumptions that underlie this argumentation. So it's got a lot of the stuff we've been talking about: the assumptions, the evidence from testing and evaluation, and then this argument, which may be a sequence of claims that you're trying to show through test and evaluation, that then gives you that justified measure of confidence that the system will function. Again, not a proof, just a measure of confidence. So how do you do that? You need an argument. So you need to understand what the argument are, what's the claims, and then what evidence are you going to need to back up those claims. And so it just links the process of building an assurance case through test and evaluation is collecting the evidence that back up claims that build a high-level argument. So it's doing the observing, analyzing, testing, simulating, that you have to everything you have to do to come to some confidence that the claim is true, and then construct the argument from your sequence of claims. And there's a nice little picture I took from this one reference that just makes it a little more visual. So the assurance case then is just, think of it as you've got the high level claim, my system is safe to operate within a certain set of operating conditions, and then, well, maybe you can decompose that into a sequence of other claims that are more easily testable. And from that, instead of just that one high level claim, and then it's just a simple, from this tree, this sequence of arguments that if I show claim 2 and claim 3 through their evidence, and that shows claim 4, just simple logic, and works me up to the final claim. And this is how you would build an assurance case. And of course, the art is how you decompose it from what the high level thing you're trying to show, and what are some sub claims that I think I can show, and that I can get evidence for, and go from there. This is something that some of your colleagues down at the Warfare Center, the Air Warfare Center down at Pax River, have been thinking a lot about for air autonomous systems. Some folks I've known and worked with, Dave Scheidt and Jeff Sappington, are starting to put together what they think is sort of a standard model of framework for building an assurance case, really. I don't know if they called it explicitly that. No, it doesn't look like it on the slide, but that's what this is. It's just a sequence of things to show that each of them needs evidence of their own, but all together, then there's basically some proof that the system you can have confidence that the system will work as intended. And so this, I think, is a great example for the specific autonomous air vehicles that they're interested in down there at NOC AD. There's a program at DARPA, too, that's looking more generally at this, building assurance cases for autonomous systems. This is Sandeep Nima's Assured Autonomy program. He was also part of our workshop a few weeks ago. And this is an ongoing program and very active research in this. But it's looking at building up from design time, so doing sort of model-based system engineering and using those models to do some formal methods, formal verification, like we talked about formal methods a little bit earlier, but also simulation-based testing. So to build evidence, basically, to do your assurance case. You can see the little tree of claims and evidence on the right there. And then he's extending it into dynamic assurance, because the challenges are in an operating environment where you need to, where you'll be encountering potentially new environments that you hadn't planned for during design time up at the top. How can I then build in that runtime assurance? I talked about runtime assurance a little bit earlier. so that you still maintain that green, essentially, assurance measure, as he's calling it, that abstract assurance measure. Your argument still holds. You've got guards in place. Guards are runtime assurance that I talked about earlier, and you'll still work within the operating conditions that you expect to encounter. And so this, as I say, ongoing. It's by no means a settled science. Any of this, that it's ongoing R&D. Okay. And that's it, actually. So as far as the actual technical talk part goes, so if there's any other questions, I think I'm at about an hour. I'm not sure exactly when we started.
Yeah, no, you're good. We have about 10 minutes left, so I'd like to. We're gonna open the floor at this point for questions, both for Dr. Lawrence and for Dr. Holmes. In case you had a question from the previous presentation, and then what I think we'll do is have a few minutes at the end and give you an opportunity to talk a little bit about ARLIS. And for those at Carderock, if there's questions that you want to follow up with, we can figure out a way to facilitate that.
Sure. And I'll leave these slides behind, by the way, so if we don't get, that's fine. If we don't get to my shameless ARLIS plug, folks can take a look at the slides too.
Yeah, well, you're conveniently located close to our home base here. So I did see someone raise their hand, so I'm going to ask a question in the Q&A first, and then if you want to ask a question over audio, you can just unmute yourself, I believe. If not, Ashley can help you with that. You can ask the question directly. So I have a question here on, there's a number of questions, but let me pick one that I think is probably relevant, highest relevancy here. So is there an easier accepted path forward when not enough data exists to properly train a model acceptable to trick the learning process? And so I personally, unrelated to the person who asked the question, I've thought about, hey, especially for systems that have physical dependence. So if there's a set of equations that describe, that process, seems to me that you can rely on that model combined with the data-driven model to kind of get you there for limited data. But what if with a human or something else where there's typically these low data environments, so there's not a robust physics-based model. What are your thoughts there?
Yeah, you're hitting on one of my especially when I was at DARPA, and folks would come and always want to say, I've got this great new learning approach that's going to solve all your problems. My first question would be, well, where are you going to get the data for that? Where's it? You're talking about, especially in our world and DoD and the intelligence community, there's a lot of things that we just don't have a lot of data for. So I'm really interested in, and you hit the nail on the head, things where you can combine more causal modeling, which I'm personally more interested in with the data-driven approaches. And I think we need to do a lot more of that. I'm a little concerned or disturbed at the trend of deep learning and some of the other machine learning approaches, where it's just more and more data and more compute resources to do things that seems like a child learns in just a few examples. So you're really hitting on one of my key topics that I'm very interested in. And then you asked a follow-up of when we're maybe dealing with humans or some other situations we haven't been in before. Is that?
No, I think my question was more is there's no physics-based model of a human, right? Or maybe some social psychologists have some representation of our behavior, but to me that was a clear area where it's not like, hey, Newtonian mechanics apply or quantum mechanics apply, so we have something that we can rely on, where we kind of know the answer. It just may be computationally inefficient to do fast enough to provide input.
So it's something we're interested in here because of some of the test and evaluation work that we want to do. We're interested in, for other reasons, starting to understand, are there useful models of people and the decision-making processes? There's a number of programs going on that are, especially when it comes to that decision-making process, and can we meaningfully do it? And not necessarily a data-driven approach. Are there some models that help us characterize the way people make decisions in certain environments under certain conditions? And it seems that there is some promising work in that area. It's not me that's doing all that work, so I couldn't point you to the literature. I could get you the person here that is doing some of it, but I'm interested in it because I'd like to use those models then to start doing more simulation-based exploration of operational effectiveness of human-machine teams. That's something that we're trying to measure here and characterize. Important question. I don't know that it's settled whether we have good models yet of people, but it is something that I think folks are trying to do better.
Yeah. No, it's a great point. I mean, I know I've touched on it on a bunch. I think the human-machine teaming piece is something that we, at least at our organization, don't tend to think about because we're not always putting a system in front of an end user. But I worked on a project a number of years ago, and we had that problem, and it was like, hey, you got to give them three answers, you know. Oh, sorry, two answers, yes or no, like maybe is not good. And so, you know, this huge existential crisis around how you do that. And it just gets more and more complex, I think, as you move into these systems where, again, we don't have as much peace. So the trust in the system will be important there. So let me pause for a second. I will give folks on the line an opportunity if somebody would like to ask a question. I don't know if they even have the capability or not. So I'll pause for a second. All right, so looks like we got a new question in here, but sorry, it's unrelated to the topic. So I'm gonna hop on a pet peeve of mine, not pet peeve of mine, a topic area of mine that I think is important. I'm getting a message here that they don't have audio capability, so I apologize. So if you do have a question, put it in the Q&A. I'm happy to translate it either for Dr. Holmes or for Dr. Lawrence. But uncertainty, you know, and I think that's at the root a lot of what I'm thinking of when we get to these human-machine teams, because as you highlighted, it's kind of that trust that builds over time because I've used it. And the thing that I've often tried to figure out is, hey, if we have a system, you know, regression or a classification model, probably some of the most use cases for machine learning that we have here at the command, less so NLP, but anyways, the question is how might you get, you know, even just confidence bands, you know, out on your answer, you know, the sensitivity of that model without having to go and perturb every single one of your inputs and look at the sensitivity output. And so I don't know if you have many thoughts there, but to me, that's, you know, one of the root problems that always becomes difficult, even for deterministic systems.
Yeah, I guess I don't have deep thoughts on how you might get them out of some of these more opaque systems, other than doing the sensitivity analysis. But it is important though with the trust issue. I've been thinking about one of the things we do think about is then how do you represent, if you do have an estimate of uncertainty, then how do you represent that, you know, in a way that's useful to users. And I worry that some ways of representing it, you know, then they take too, I hate to say it this way, but non-sophisticated users may take too seriously and think, well, if you put an error bar there, then that it's definitely within those, and they don't have a good way of interpreting what does uncertainty mean if I give them a variance or something like that. You know, how do you represent it and display it? That is something that some folks here in the human computer interaction world are looking at. But actually teasing it out, which your real question, that wasn't that. It was actually how do you extract it from these systems when they don't provide it for you? And I can't imagine. I personally, Craig, can't come up with a better way than just doing some sensitivity analysis. Yeah, sorry.
Thanks.
Better answer.
No, and it's just you know, something to think about, because you know the scariest thing is you deploy a system and somebody says, well, I no longer trust it, so I'm just going to ignore it, and then you've lost you know, capability there.
Yeah.
So
Great.
So I have 1 minute left by my watch. The slides will be made available to folks. So those who are interested more in ARLIS, you can find them online just by searching. They're nearby. I'm going to look to reach out to you to have some conversations about how we might be able to partner some more in the future. But I'd like to thank all three of our presenters today. So it's going to be Dr. Holmes, Ms. Shields, as well as you, Dr. Lawrence, for taking the time and coming to talk about a wide variety of topics that I know will keep me thinking about these topics for a while. So thank you, and I'll hand it back to Ashley to close us out.
Just wanted to thank you guys for joining. Yes, this has been like a good presentation. So I was like doing stuff in the background, so I got my mask on at the Naval X facility. But yes, happy Engineers Week to all the engineers, scientists, technicians, math, and then people that have everything in between. We thank you guys for joining us. And this webinar is also going to be available to view afterwards, so you guys can share it. I think we're able to put it now on Fusion, so we want to really get active involvement on Fusion. And we thank you guys for joining us today.